In this lecture, we're going to learn a little bit more about MIPS memory. We've already learned the basics and how to use it. Today we're going to learn what we're allowed to store where. First, we're going to learn about the MIPS memory map, which tells us where we can store different types of data. Then we're going to learn how to turn a program all the way from text into something that you can actually run on the computer. So we know that MIPS memory has 32-bit addresses and is byte addressable, meaning every byte has an individual 32-bit address. Given that, how many bytes can we address? Turns out that there are 2 to the 32 different places we can address in MIPS memory. What's the maximum address label we can hold? In binary, it would be all ones. So in hex, it's going to be all Fs. And so there need to be 8 of them, because each hex digit is the same as 4 binary digits. So this 8 Fs is equivalent to 32 ones, which is the maximum address. And as a reminder, even though memory is a byte addressable array, we usually draw it laid out in a rectangular pattern, which is 4 bytes wide. 4 bytes, because each word in MIPS is 4 bytes. So addresses 0 through 3 all correspond to the same first word. The MIPS memory map splits memory up by topic. The main distinction is between instructions and data. Within data, we then split it between global data, or static data, which is allocated before the program runs, and dynamic data. Global data would be something that we could put in the .data section of our MIPS assembly. Dynamic data is something that would be accessed via the stack or a syscall. So the actual MIPS memory partition looks like this. We cover all the addresses up from 0 up to the end. At the top and bottom, there's some reserved sections for the operating system. We then have the distinction between the text below this line and the data above it, this small section for the global data, and this much larger section for the dynamic data. We'll talk about each of these sections in turn. The text segment, which goes from this address to this address, is where the actual assembly language, where the actual machine code is stored. So when we convert assembly language into all of its ones and zeros, we then put it into this spot of memory. You'll notice that every address in here has a leading 0 in hex, which is the same as 4 leading zeros in binary. So the 4 most significant bits are 0. Given this address range, think about how much code we can store. This is going to be a problem on a lab later on, so I'll let you ponder it. Also think about how this might impact the jump instruction. If you recall from a previous lecture, we said that the jump instruction always assumes that you're jumping to a place with the same 4 leading bits as the current program counter. We now know that every line of code has the same 4 leading bits. They're all zeros. So in fact, the jump instruction can take us anywhere we want to go in the text segment. The global data segment is for data that we know we want to allocate before the program even starts. Any function can access this. Based on the addresses, we can see that this allows us to store 64 kilobytes of global variables. In the middle, pointing to the middle of the global data, is GP, the global pointer. The reason that we have this is so that we can access things in global data more simply. Looking at the possible addresses here, we can see that they have the same leading 4 bits, and the trailing 4 bits go all the way from 4 zeros up to FFFC, which then would be FFFF at the end of that word. And so this differs by 16 bits. So anytime we want to access something in global data, we can do a load word, put it wherever we want it to go, And then with some 16-bit offset of the global pointer, we can reach anywhere we want to go. So that's why we have that global pointer. It allows us to access everything in global data with just one command, because all of those 16 bits immediates can be represented by that. The dynamic data segment is by far the largest portion. This drawing isn't to scale. You can see by looking just at the leading numbers that this goes all the way from hex 1 to hex 7. So it's the vast majority of our memory. At the top is the stack, with the stack pointer starting off here, which was discussed in a previous lecture. And then at the bottom is the heap. So the heap is where we would get things where if we used malloc in C or new in something like C++ or Java, the operating system would give us some space, and then we could use it in all sorts of different functions. We need the operating system to handle space in the heap for us, because whereas the stack grows nicely, it'll go down as functions are increased, and then once you finish a function, you just go back up. The heap doesn't work like that because it's available to different functions. So you might allocate some space in the heap, and then later on, if you don't need this bottom part anymore, you might free it, leaving empty memory at the bottom. It's difficult to keep track of things like that, so the operating system usually handles allocation of memory on the heap. With the heap growing up and the stack growing down, they can eventually run into one another, in which case you would suffer memory corruption. So the operating system also tries to avoid having this happen. Finally, there are the reserved segments at the top and bottom. These can't be used by your MIPS programs. The operating system has to live somewhere on the machine, and this is where it puts its information. Now that we know how MIPS memory is laid out, we know everything we need to know about getting a program into memory and actually starting it up. All the way from taking high-level code, such as Java or C, down to getting it into memory and actually running it. And we'll talk about each of these parts at least briefly. First is the compile phase. This is where you take your C, Java, or whatever else code and turn it into assembly code, or more likely, have a compiler do it for you. Once we have assembly code, we still can't put it directly into memory. We have to run it through an assembler. This needs to be done in 2 passes. The assembler goes through, assigns an address to each instruction, and looks for labels. For example, main, which might indicate a line of code, or F, which is indicating a global variable. Each of these needs to be assigned an actual address. Once you've done that, you can take your machine code and your symbol table and put them in an object file. You're still not quite done. Typical programs aren't monolithic. They're not all written in one giant text file. You're almost always calling out to another library or other files that you've written. Because of that, you need to be careful with your symbols. For example, F in one file might mean something different than F in another file. Also, 2 different addresses, 2 different instructions may have been signed the same address in the assembling phase. The linker needs to take care of these conflicts in a way that makes sense. After that's done, you have your actual machine code. And now we know where to put it. So once you have your machine code, you put it into the text segment of memory with the first instruction starting off here. You put your global variables into the global data section, and nothing goes into the dynamic data section yet, because again, that's allocated at runtime. After that, you simply set the program counter to the correct value, and the machine runs as normal. So that's the entire process of getting a program all the way from source code into actually running on your machine.